Welcome back. This is the second segment of section 6.3. We were in the middle of solving some multiple angle equations, and we're just going to pick it right up and keep doing some more. I'm trying to keep these videos down to 15 to 20 minutes, and I think we were at 17 and a half, so let's see if we can pull that off again. That's probably just about perfect to keep people's attention. So we are in, I think we're on page 3 now, and I want to pose another equation that involves multiple angles. So cosine of 2x times sine of x plus sine of x equal to 0. Okay, this one is actually deceptively easy. There's not much you have to do here except recognize that this is factorable. Notice there's two terms. There's a greatest common factor, which we can pull out immediately, sine of x, and what's left over is this cosine of 2x plus 1. And that's all equal to 0. So this again leads to two solutions, or two separate equations, sine of x equal to 0 and cosine of 2x equal to -1. Okay, so here the solutions that we're going to get are the inverse sine of 0, which happens to be 0, its supplement, and then all coterminal angles. So since we've done that particular one a couple times, I'm just going to write down the answer. So you've got 2 pi times n, 0 plus 2 pi times n is going to get you this. Or we have x equal pi plus 2 pi times n. Okay, there's your two solutions from sine x equal to 0. So this one I'm going to take a little bit more time because note that the inverse cosine of -1 is actually pi. We're not going to get as many solutions out of that because it happens to be its own negative in terms of the angle, the position of the angle. So, but if we recognize that at 2x should be plus or minus the inverse cosine of -1, which happens to be pi, and add 2 pi times n, okay, then when we divide by 2, we get x equal to plus or minus pi over 2 plus pi times n. Now we suddenly get some extra solutions. So if we were predicting how many solutions we could possibly have, my prediction would be that there's up to 6. It turns out that in this particular case, I think we're going to lose 1 or 2, but let's just start writing them out. So x must be a member of this set that contains, well, this one is 0. If you put in n equals 0, you get one value of 0. For this one, n equal to 0 is going to give you pi. You won't get any more solutions out of this because everything else will be too big. Now, for the cosine terms, let's consider first the positive branch with n equals 0. So we got pi over 2. And then we can add n equal to 1. We'll get 3 pi over 2. And this is where I think we're going to start getting some multiplicity issues. So if we then look at the negative branch, well, negative pi over 2 is too small. So when we add pi to it, we get pi over 2. See, we're getting a repeated root here. And then when we let n equal 2, we're now adding 2 pi to negative pi over 2. That's going to give us 3 pi over 2. And again, you're seeing this multiplicity of this root. It is purely because of this being -1. If this was some other number, you would get some kind of a screwball angle in here, and these would actually produce 2 more solutions. But that, like I said, that's comparable to what they call a multiplicity of a 0 in algebra. Okay, so let's try the next one here. Maybe a little bit more challenging. Let's go with sine of 2x times sine of x minus cosine of 2x times cosine of x equal to minus cosine of x. Well, this looks kind of awful. What I'm seeing here is that this is an expression for cosine of 3x, but I'm not really sure how that helps. What we could do is we could do some trigonometric substitutions and try to see if this thing cleans up a little bit. So I'm going to leave this over here alone. I'm going to make the substitution for, because I think what I'm going to try to work towards is a polynomial in cosine of x, so which we could use those techniques. But I'm a little concerned about this right here, because if we end up with a cubic, maybe it'll be factorable. Let's just see what we get, because we don't have any constant terms, which is nice. Okay, so first off, let's make the substitution here for sine of 2x. So that's going to be 2 sine of x cosine of x times sine of x. And I'll make the substitution for cosine with the version that only has cosine in it. So 2 cosine squared of x minus 1 times cosine of x. I'm going to leave the right-hand side alone for a second. I'm not going to do anything over there, so I'll just put ditto. Now this is going to collapse into 2 sine squared of x times cosine of x. This is going to break up into 2 terms. I've got minus 2 cosine cubed of x, and then minus plus cosine of x equal to minus cosine of x. And I'll make a substitution for sine squared using a Pythagorean identity. I know this is getting a little bit ugly, but I can push that cosine to the other side for the time being, or bring this one over here, collect them into like terms. So maybe I'll do kind of both of those things at the same time. So I've got 2 times 1 minus cosine squared of x times cosine of x minus 2 cosine cubed of x plus 2 cosine of x equals 0. Now distribute again. Notice I'm going to get an additional 2 cosine x here, and I'm going to get an additional minus 2 cosine cubed here. So it's like this whole term is equal to that whole term, and they just kind of double up. But let me write that out in a couple steps. So 2 times 1 times cosine. So I've got 2 cosine of x. And then 2 times minus cosine squared times cosine is going to give me minus 2 cosine cubed of x. Then, of course, the terms we already had are identical. Minus 2 cosine cubed of x plus 2 cosine, should be 0, cosine of x equal to 0. So let's clean this up a little bit. Combine like terms. We now have minus 4 cosine cubed of x plus 4 cosine of x equal to 0. And I can do some things with these coefficients to make this a really, really simple looking equation, which is just cosine cubed of x plus cosine of x equals 0. Now, this is the kind of stuff, I know there's a lot of steps in there, but this is the kind of stuff that we did in chapter 5. And this is the reason why, because now that this thing is down to a relatively simple form and something that we can kind of see our way out of this, we can actually solve this equation. So I'm going to move to the next sheet of paper and just repeat that as a kind of a new problem almost. This is page 4. Okay, so we're wanting to solve cosine cubed of x. And I think I think I made a slight mistake here. The SIGN should be different on this. Should be minus. Okay. So cosine cubed of x minus cosine of x equal to 0. And this is ripe for a factoring technique, because if we didn't have if we weren't able to factor this, I'm not sure how we would do it. We'd have to pull out a CRC manual, and I'd have to remember how to solve an arbitrary cubic. But fortunately, this one was going to work. So when we pull out the greatest common factor, that happens to be cosine of x. And what's left over is cosine squared of x minus 1. Okay, so this, we haven't done much with this sort of thing, but this leads to cosine of x equal to 0, or cosine squared of x equal to 1. These solutions, so remember cosine is equal to, we did, I think that in the last one we had, well, maybe not. So cosine is equal to 0 at pi over 2 or negative pi over 2. I'm just going to go straight to the answer. So x is equal to plus or minus pi over 2 plus 2 pi times n. This one I'm going to spend a little more time on because the tendency here is to want to take the square root of both sides, which is the right thing to do. However, you got to remember it's going to make this plus or minus, which actually leads to two equations. So we have cosine of x equal to plus or minus 1. Now, this looks like maybe you could do something easy, but you can't. You now have to write two different equations, cosine of x equal to 1, which since we have done this a couple times, I'm just going to go straight to the answer. Notice cosine of x is equal to 1. This is this multiplicity business. It's only going to be 0. So x will equal 0 or a coterminal angle. So 2 pi times n. And then we have this, from the other branch, we have cosine of x equal to negative 1. And that was, we kind of solved that last time, but I think we can go straight to the answer. X is equal to pi plus or minus pi plus 2 pi times n, and we're going to get some multiplicity there as well. So to summarize, then x is if we're going from 0 to 2 pi, let's start peeling off the answers. Here we have pi over 2 is one answer, and 3 pi over 2 is one answer. So pi over 2, 3 pi over 2. Okay, here the only answer we're going to get that contributes is 0. And here the only answer we're going to get that contributes is pi. So it's possible we could have had two more solutions, but that's it's only because we had some issues there with multiplicities. Okay, so let's try one. We've done, everything has been sine and cosine. Let's do something with maybe one that's not so pretty. Do I really want to do that? Yeah, let's go ahead. This may take a little bit of space here, but so let's try cotangent of 2x minus cosecant of 2x equal to 1. The reason why I'm barfing at that is because we don't have a good we don't have a good version of these double angles for these particular functions. But what I'm seeing is that we can probably square both sides and pull out a Pythagorean identity. We have to make sure and get them on the right side. So let me think about this a second. If we move it to that side, we switch those up. Yeah, here's what I'm going to do. I'm going to rearrange this so that the cosecant is isolated. So we've got cotangent of 2x minus 1 equal to cosecant of 2x. And then I'm going to square both sides. I always do this because I want to remind myself I got to check all the answers every time I do that. When I square both sides, remember I'm going to have to FOIL this thing out. So I'm going to get cotangent squared of 2x minus 2 cotangent of 2x plus 1 equal to cosecant squared of 2x. And here's where I'm thinking I'm gonna find a quick answer. This looked harder than it really was, because once you do this, notice cotangent plus 1 is actually equal to cosecant squared. So I can make that trigonometric Pythagorean identity substitution here, and I'll have the same thing as what's on the right. So this middle term has to equal 0, but I'll do that in steps so you can see it. So I'm combining I'm combining the cotangent squared plus 1 and writing cosecant squared of 2x minus 2 cotangent of 2x equal to cosecant squared of 2x. And now cancel that from both sides. I'm left with minus 2 cotangent of 2x equal to 0. Or equivalently, cotangent of 2x equal to 0. Now we've solved problems like that, except when we had a different argument when it was just x. So we just have to be a little bit careful there. Remember with tangent and cotangent, this is relatively simple. You just have to find that first root and then you change the periodicity. Well, now we're going to change it some more. So from the cotangent relationship, you're going to get that 2x is equal to, well, cotangent achieves the value of 0 at pi over 2. So that's our sort of starting point. So pi over 2 plus pi times n. And then when you divide by 2, you get x equal to pi over 4 plus pi over 2 times n. And I'm just going to, this is the last problem I want to do in this segment, so I'm going to put that right here, the solutions. I'm a little crowding here. I don't want to start a whole new page for this. But let's go back and check all these solutions. So pi over 4. All right, so pi over 4, you know that there are 4 possible solutions that come out of this. Pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. It's just adding multiples of pi over 2. So let's go through them one at a time. Pi over 4. Well, when I plug in pi over 4 here, I get pi over 2. So this cosine is equal to 0. Cosecant of pi over 2 is equal to 1. Is that right? I think that's 1. Yeah, 1. So you've got 0 minus 1 does not equal 1. So pi over 4 is out. And I think we're going to have a couple of those that do that. So 3 pi over 4 is our next one to choose. So 3 pi over 4 times 2 is going to be 6 pi over 4, which is the same thing as 3 pi over 2. Cotangent of 3 pi over 2 is 0. Cosecant of 3 pi over 2 is actually equal to -1. And so 0 minus a -1 is equal to 1. That's good. I think we're going to have every other one is going to work. So now going to the next one. So that would have been 3 pi over 4. So now 5 pi over 4. So 5 pi over 4 times 2 is 10 pi over 4. Let's normalize that. So we'll take the equivalent. 10 pi over 4 is actually 5 pi over 2, which is more than 2 pi. So normalizing that to between 0 and 2 pi, this is equivalent to cotangent of pi over 2. And that's going to be equivalent to cosecant of pi over 2. And notice that was where we had the problem before, right? We had 0 minus 1 does not equal 1. So 7 pi over 4 is out. 5 pi over 4 is out. The last possible choice is 7 pi over 4, and I'm pretty sure it's going to work, but let's go through it. So 7 pi over 4 times 2 is 7 pi over 2, which when we normalize that is going to be 3 pi over 2. So cotangent of 3 pi over 2 is the equivalent, minus cosecant of 3 pi over 2. So that was the one that worked before. We had 0 minus a -1 equal to 1. So the other solution then is the 7 pi over 4. Now, I know I went through that a little bit quickly and without a lot of explanation, but I think if you go back and check, the problem is we squared both sides. When we square both sides, we're likely to produce solutions that aren't really solutions. And so when you go through this list, you just need to check them. Now, what you could do is you could just plug it into a calculator and see what you get it, because it's a lot easier than trying to think about, finding coterminal angles and exact values and everything else. But the problem is those are functions that don't have a button on your calculator. Anyway, so kind of an interesting problem. These are the last of the multiple angles. I'm going to come back in session 3 and do some half angles. I don't know, they're not really all that exciting because they actually produce less solutions, which is kind of boring, but we might do a couple of those. Okay, I'll see you on the next video.